Good afternoon, everyone, and welcome to another Quanzer Live webinar. I'm Murtaza. I'll be your host and moderator today. This is our last webinar of the webinar series with California State University, and we are honored to have some great guest presenters here today. This week, we have Dr. Naveed, Associate Professor of Aerospace Engineering, Dr. Nolan, Associate Professor of Mechanical Engineering, and Dr. Marco, Assistant Professor of Aerospace Engineering, all from Cal Poly Pomona. In this talk, they will take a deep dive into curriculum development and industry collaboration at Cal Poly Pomona.
Thank you, Mr. Sam, and welcome everyone to today's presentation. I'm going to go ahead and share my slides. Hopefully everybody can see this. So I just want to say good morning, good afternoon, good evening, everybody, and I'm thrilled to welcome you to today's presentation, which we titled Unlocking Potential Industry-Driven Curriculum at Cal Poly Pomona. My name is Naveed Nekjiri, and I am delighted to share some insight to the way that we are thinking that this is the innovative behavior of approaching education and workforce development at Cal Poly Pomona. Joining me in this discussion, I have two of my colleagues, Dr. Nolan Sushia and Marco Medja, that are going to share the presentation with me, and two other colleagues, Ray Hudson and Shikuka Mirzai, which are not going to be in the presentation, but I am sharing their slides and will share their experience with you today. What we want to talk about today is more on exploring what Cal Poly Pomona is doing in terms of partnership in industry and trying to bring experience for our students to the classrooms and labs. And this is basically just an introduction of what we are doing, everything that we share today. There's a lot of discussions that we can have around it. So hopefully there is more to share in the future, and if you're interested. We're going to talk about the teaching philosophy at Cal Poly Pomona, how the industry role in designing curriculum and designing our labs shapes the way that we think about what we are doing and what we are going to do in the future. And we are going to think about how we are shaping the future of engineering education at Cal Poly Pomona. I'm going to go ahead and just do a quick introduction of all of these. First of all, my name is Naveed Nekjiri again. I am a professor in aerospace engineering at Cal Poly Pomona. My field of expertise are mostly in space mission design, spacecraft design, and systems engineering. And so that being said, this is why I'm very interested in this particular topic that joins what the industry is doing and what we are doing at Cal Poly Pomona in terms of teaching and educating our future engineers. So there are a few elements of the Cal Poly Pomona that I want to start with that kind of gives you a reason for why this talk is important to us and how we are at this point and thinking about the future of education. One is about the Cal Poly Pomona philosophy. So if you know about this, probably this is kind of familiar to you, but Cal Poly Pomona is very big on what we call learn by doing. And this is a polytechnic university. Learn by doing was a core of this university from the beginning, and we are still thinking about how it is going to translate to the future of education, and we are still experimenting with what we can do with the technologies that we have right now. So that is one of the reasons that industry is very important in the way that we are designing our teaching and research here at Cal Poly Pomona, because learn by doing means that we want the student to get the experience that is going to be helpful for them when they graduate from the program. We have a very big undergraduate research, and undergraduate research at Cal Poly Pomona is the way that we do all of our research, most of our research. We have graduate programs too, but the number of undergraduate research programs at Cal Poly Pomona is significantly larger. And by doing that, we started creating something that is called the teacher-scholar model that tells us how we can use our time as a teacher and time as a researcher together to shape the student's educational outcome, and also to bring more of what we do in terms of research into our classrooms. And this is kind of a core of the design of our labs, and you will see some of the examples today. And not all the labs are teaching, and not all of them are research oriented, and they are basically a mix and that's my intention. And last elements that is kind of shaping the discussion today for us is the role of our active industry advisory board. So each department is going to have an industry advisory board at Cal Poly Pomona, and they are basically helping us to design the curriculum, the teaching materials, the things that we are going to share with the students, what they need to learn when they graduate from the program. And it's a very close connection. So I'm going to talk about all of these a little bit more throughout the discussion today, and my colleagues are going to also give you examples of some of these elements. But I wanted you to have an overview of what is defining principles of what we do at Cal Poly Pomona. Of course, today's discussion is more on how the industry is going to influence the curriculum design at Cal Poly Pomona. So I'm going to highlight the 3 elements over here. So one is our active engagement with the industry advisory boards. As I said, each department has its own. We meet multiple time per year with our advisory board. This is just happens to be our advisory board at Aerospace Engineering Department, so you can see my pictures too. We basically identify areas that we need to improve our program. We ask them to provide us direct feedback on what we need to do and what we need to add. And they help us to define the visions, goals, objectives, and anything that comes with the program in a high level. So this is a very interactive meeting. As I said, happens multiple times per year. And through that, we've learned what the industry wants to do. We also have a lot of collaborative projects with industry partners. So this is through funded support that comes from the projects that we get from the industry. We have a lot of those that are coming to our clubs, coming to our research labs, and coming to our projects and capstone projects. And we also have a lot of partnerships on writing grants and trying to, find other resources to create research labs and research partnership with industry. And that's kind of what a lot of universities do. But at Cal Poly Pomona, we have the benefit of being in a very active industry driven region, especially in my field, aerospace engineering, that in Southern California, we have a lot of companies and a lot of interest in investing in research projects. We also have a lot of design classes and taking students to the industry to present. So industry does a review and serve as a subject matter experts for us. And that is another way of understanding what they want to see in students' projects and students' research. And based on that, we also adjust what we teach in the classes. And finally, we are also lucky to have a lot of people from industry to come and teach for Cal Poly Pomona as adjunct faculty. And Ray Hudson, one of the colleagues that is sharing some materials today for us, is one of the examples that they have a very close partnership with Cal Poly Pomona at some point through any means, and then they started thinking about what else they can do, and we always invite them to come and teach courses that are specialized in their areas. They bring their tools, they bring their expertise, and that way we are expanding on not only the knowledge of the students, but also shaping the entire curriculum for the department. So these are kind of 3 different areas that I wanted to highlight how the industry influences the way that we design the curriculum. So one of the elements that you will see throughout the entire examples of today's are around the model-based design. And the reason for that is because the industry has a very high focus, or basically a very special focus on the model-based design in the recent years. So what we are seeing in the industry, and I'm going to give you some examples from the industries that I am familiar with, looking at Air Force and the Department of Defense. If you're looking at their documentations for what they call the digital building code, you will see that all of them are mentioning things that they require now all contractors to have. And now all contractors, they have to look into designing digital twins, designing digital modeling and things that are going along with their process and with their actual physical models that they create. So this becomes kind of a standard in industry. And since Aerospace and Department of Defense, they fund a lot of projects and a lot of industries in the US, they are basically giving this instruction to everyone that consider these as kind of a requirement for anything that you do. Now, if you think as an educator, this is where you have to, bring this to the classroom and teach the students how to think about the digital environment and digital building models and digital twins in general. We also have a lot of push from the industry in terms of model-based systems engineering, which is something that is kind of familiar for aerospace engineers because they have to do this for a very long time in most of the industry partners. But now you see that model-based systems engineering is actually expanding to all the other aerospace, all the other engineering areas. And some of the main frameworks that are at the core of the model-based systems engineering, like the Department of Defense Architectural Framework, or the system model language that is now in version 2, which are helping us to create these model-based design environments and trying to connect that to the systems engineering aspect of design process. These are all kind of framing the way that we want the students to also learn engineering as well. We are thinking about, the traditional teaching environment versus the model-based design-focused environment. Of course, what you need to bring to the classroom is to understand how the digital models are going to work, understanding how the hardware are going to work, and then understand how they can work together. This is an example of what we are doing at Cal Poly. So we have a lot of modeling tools, but MathWorks is probably one of the most common one that we see in engineering programs, that we teach students how to work with the simulation model, with basically creating this environments that can mimic the actual hardware or actual software that they are designing. And they can run simulations through this platform, but now we are adding a lot of hardware that goes with them. So Quanzer is one of the partners that we have a lot of equipments, and some of the examples that you see today, or most of the examples that you see today, are basically the collaborations that we have between Quanzer and MathWorks in terms of teaching model-based design and then bring the hardware in the loop for our students to learn better. So we are going to have 4 case studies for today. Each one is basically prepared by one of my colleagues. We're going to talk about the feedback control lab, and we're going to talk about the mechanical control. These are the 2 that we already have established at Cal Poly Pomona, and students are using this, and it has been a great experience for us. But then the other 2, the astronautics lab and smart manufacturing lab, these are what we are doing in terms of partnership with Quanzer and MathWorks in order to develop the future of the laboratories and smart, innovative projects and research that we can do with these methodologies. So feedback control lab, kind of similar to a lot of other curriculums. We are teaching control, but it's based on that idea of the learn by doing. We want the student to learn exactly what is a control system by applying that to a hardware. So they learn through the software and modeling, through the Simulink, and then they apply that on the hardware, and they start experimenting with all of these relationships. We're going to focus on the mechanical control lab, on the teacher-scholar model, that we are using this as kind of between teaching and research, and the hardware and the modeling that we have in there is going to support that. On the astronautics lab, we are going to talk about the digital twins and the future of digital twins and how it can make us able to do virtual testing and virtual experimentation. So that's one of the cores that we are going to share. And then we're going to talk about the smart manufacturing lab. And we are seeing how we can create an industry level manufacturing modeling with hardware and software, and how we can in the future use some of the technology and algorithms that comes in machine learning and AI in order to optimize these kind of manufacturing process at Cal Poly Pomona for students to learn as well. So I'm going to start going through the first case study. This is the case study that my colleague Ray Hodson has created. Ray is a practicing aerospace engineer. He has been working in the aerospace industry since 1985. And his main areas are in aircraft performance, in flight controls, in guidance navigation. And over the last 15 years, he has been very active in designing model-based systems engineering models and teaching these to industry, and also at Cal Poly Pomona as an adjunct faculty. And he's now serving a lot of aerospace companies as a consultant. So what we want to share about this experience is how we improved our feedback control lab in order to follow this exact model of learn by doing and bringing these techniques into our classroom. So this is just an overview. I don't want you to necessarily read through everything that I have over here, but this is typically a curriculum that you see in any controls, a feedback control class in the undergraduate level. The thing that is important to us is that we don't just teach the theory. We also have the lab to go with the theory. So as the students going through the theory of control, they also learn about how to implement those theories on a modeling front, which is going to use Simulink model, and then how they can apply that on hardware that in this case is going to be a Quanser hardware, that we are going to show them how those control algorithms are going to be applied to a hardware and how there is a connection between the design that they have and what they see and the experiments that they do on the hardware, and they can compare the real-time response of a system this way. So this slide just giving you a list of what we cover in a typical control class. And this is at the junior level for our programming aerospace engineering program. So what we did is that we actually started thinking about what the industry needs. And this is coming from the industry itself. As I said in the industry advisory board, they tell us that industry likes to see MATLAB and Simulink as the leading control system design analysis tool. And a lot of aerospace engineering companies are using this as their baseline for a lot of design. So we had to bring this into a classroom, and that's the core of the controls class that we teach at Cal Poly Pomona. Now, they want the graduate students to be able to work on the control systems, not only understand those concepts, but be able to actually design a control system. And this is where the Simulink and MATLAB is going to be very helpful for us. They need to understand something that we refer to as a closed loop learning, which means that they can, basically bring everything to a final design and then do an experimentation, understanding the modeling, understanding how they can check their work, understanding how they can validate these models. And we want them to be able to explore more complex problem using these tools. And that's one of the benefits of model-based design that allows you to actually add to the complexity of the system, still get a lot of interesting results out of it. And we want to have also student-to-student learning experience, because when we are doing this in a classroom and in a lab environment, we actually encourage the students to work together to fix a model, to troubleshoot a model, and then even work with each other to learn the way that they are modeling. So just to give you an idea, this is a typical flow of the courses that the students in our curriculum is going through. They first learn how to work with MATLAB as a programming language in their first classroom, as you see over here. Then they go to the feedback control. In feedback control, they learn about the Simulink and how they can do model-based design. And eventually they go to much higher classes like aircraft or spacecraft dynamics and control, where they apply these control theorem that they learn. They apply these learning that they had based on the lab experiments into a much more complicated systems. But in order to support this, we also have some other elements that comes in handy over here. As I said earlier, for the control class, you have the control lab over here that helps significantly in terms of understanding all of those theories. But even for learning how to do programming, how to do model-based design, how to work with Simulink, we also have our systems engineering class that kind of provides the framework of thinking about the systems in a complex sense and how you can think about different elements of a model that helps you to design very complex systems. So that's basically what we are trying to do. And what you see over here is, again, kind of the result of an industry-driven curriculum design, because they want to see the students to get all of these knowledge and expertise and skills, not just in one area or on one theory. They want a comprehensive understanding of how the system is designed in general. And this is our way of basically bringing that into our classrooms. So now, with the new addition that we had, so recently we had the opportunity to upgrade our control lab, and we started looking into the aero devices from Quanser, and this is what we have set up right now at our lab. So we have multiple of these stations for our students that now not only they have to design the experiment in Simulink and run the experiment through Simulink and get the numerical data, but then they have to apply that on one of these hardware and basically bring the hardware in the loop. So hardware-in-loop integration of the Quasar devices is actually very important for our students now, because they see how industry is actually doing that. And this is what is a standard, that you design a model, then you bring the hardware, you do the testing and verification and validation for the entire system before you can actually apply that to a much larger system. So one of the things that we do is that we give the students the ability to test their control system design on these platforms, and they also learn how to compare the experimental data with the numerical data. That's part of what they're learning over here. As I mentioned before, they understand how to do real-world troubleshooting when they see a problem in the hardware, and they can go back into the model and try to fix it. And so right now, there are 6 experiments that are core of that course that I showed you, the feedback control systems that the student learn about how to design the models in the Simulink, bring that on the hardware, and then test it on the hardware. So this is kind of a typical feedback control system, but we have this engaging and interactive experience by students to go through this software and hardware. So one of the things that I want to show over here is that many of these elements that I didn't go into the details of it actually came out of our collaboration with the US Air Force Research Lab. And we have a very good relationship with the AFRL, the Air Force Research Lab, and a lot of money and funding that we have for upgrading these labs, they come from the AFRL. Now, they are the big promoter of model-based design and model-based systems engineering, and that's what we are trying to do over here. So recently we had another big grants from the AFRL to help design our liquid rocket lab. We have a lot of funding that came to us to be able to build the control labs that you just saw an example of it. We are now working with the AFRL to bring the model-based system engineering courses into all of our classes, not just as an individual course that is now taught at the senior level, but even from the freshman, sophomore, and junior level, they should learn elements of this model-based systems engineering throughout the course. And the control class was one example of that. So I want to also mention that we are also experimenting with a lot of different tools that are able to help us with modeling. Of course, MathWorks and MATLAB Simulink is one of the tools that the students learn very quickly and very easily in the curriculum. But we are also looking at industry level tools for model-based design and model-based systems engineering, like Cameo and Siemens and AFSIM, and also the Genesis, which are tools that are used for model-based design. So this is just giving you an example of what we do and how we end up being at this point in our design. But for the next one, I'm going to pass the presentation to my colleague, Dr. Nolan Sushia, and he's going to talk about his lab.
Yeah, thanks, Naveen. So I'll just talk briefly about my experience with MathWorks and Quasar. I'm from a different department. I'm from mechanical engineering. Our emphasis is very different from the aerospace, but we share some commonalities across the curriculum. My area of expertise is in dynamic systems and control, and that's probably about the extent of the overlap between mechanical and aerospace. But nonetheless, Dr. Naturi and I share a lot of just the same thought processes on how to teach these courses. So what I'm going to do is just go ahead next, Naveen. Just introduce myself as well as the lab that we recently built out using MathWorks and Quasar products. So I want to take just a minute to emphasize the teacher-scholar model, because I feel like most universities probably have something similar to this, but at Cal Poly Pomona anyways, this is sort of explicitly encouraged. And this teacher-scholar model is nothing but, it's just a framework that encourages integration of scholarly activities into the classroom, really to familiarize and incorporate undergraduate students into scholarship. So whether that means bringing some new findings or new results into the classroom, and keeping students up to date on current events in our particular fields, or actually doing undergrad research outside of the classroom. Now, all of that kind of falls under this umbrella of the teacher-scholar model at our university. And so one of the things that we try to do in order to implement this sort of idea in the classroom and in scholarship is to provide students with modern tools to bridge that gap between, you know, their lectures in college and then, you know, their first job out of college. So we really require and is sort of a necessity to have a modern laboratory setting so that they get used to the tools that they're going to be using outside of once they graduate. Next, I mean. So this is kind of silly. There's a picture and a picture of the same picture. But recently we had the opportunity to secure some funding. Dr. Nakjiri and I received a grant from DoD a couple of years ago. And the primary use of that was to build out our undergraduate controls laboratory. Now this is the way that the photo's taken, it looks like a large space, but it's actually a relatively small space. And like, all faculty have the same kind of issues where we run into space, right? We just don't have a ton of space on campus. So all of our labs sort of serve two purposes. We don't have separate instructional labs and research labs. They're all in the same room, which is kind of a double-edged sword. There's a silver lining in that because it tends to bring together the academic side as well as the research side. So we'll have master's students working, on some of the equipment, just as an undergraduate laboratory is leaving their classroom. So there's a little bit of crossover, which is actually kind of nice. It's sort of a blessing in disguise. So this is our space. Next, Naveen. And so the things that we have outfitted this lab with are 10 of these Quasar cubes, and I'll speak in detail how we use these particular hardware in detail in just a minute. But we've got 10 of these Quasar cubes, next, as well as 6 of these Cubots. Now these are sort of open source, just general robotic platforms, which is really nice. Next. And then we've also got 6 of these, that's too far, next. 6 of these Quasar Q cars. Now these are really powerful research tools, and I'll speak in more detail about these in just a minute. But the grant that we received kind of covered the cost for all 10 of the cubes, as well as 6 of the Q bots and 6 of the Q cars, along with a very powerful PC workstation and all of the software licenses needed to run the specific hardware on all of the 8 or so workstations. Next. Okay, so like I said, our lab is dual purpose, like most of the labs at CPP. Our instructional laboratory, this is essentially our classical controls course in our curriculum. Now, not every mechanical engineering department in the country will have a controls course as a required core course, but we do. And so developing this lab was kind of important because prior to 2020, we actually didn't really have a set controls lab. So we had some lab space, but a lot of the projects that were meant to reinforce the lecture material for this controls class were just project-based, where the goal was for students to build some type of project and then, do some feedback control using whatever peripherals they had. And typically that would end up being some Arduino projects, which not only are students not focused on the core academic concepts, they tend to get bogged down in the details of just learning how to, write code in Arduino and building, there's a mechanical aspect to it. And so there's very inconsistent laboratory experience across students within a section, as well as all the other sections of the course. So being able to transition over to the Quasar Cube Servo 2 platform has given us this fantastic advantage where all of our students are now getting a consistent experience within the section as well as across all of the sections. Now what you're seeing here is basically just a box. It's just a DC motor. It's essentially a DC motor platform, but all of the hardware and the integration and the interface between this box and MATLAB and Simulink that's just rock solid. That's essentially the value proposition of the YOUser hardware, is you get that just turnkey right out of the box. You can start running feedback control, start doing some PID control, and all of the other topics that are listed here. So the idea is that students would take the lecture, learn about, say stability or, Ruth Hurwitz design, or learn about root locus control design, and then they can go straight into the laboratory and do an assignment or a laboratory exercise that would reinforce this concept. So it's been actually very useful. We've got feedback from the students. Probably the richest data set were some of the students who didn't, they didn't make it through the first time around. And then they were part of the first cohort that transitioned over to this new hardware. And the feedback from those students was just phenomenal. Like, they really appreciated the fact that all the labs were consistent and very clear on what the outcomes were. So this has been one of the biggest sort of benefits of this grant, is to get these YOUser cubes into the laboratory. Next, Naveen. And then we've got we got other hardware. So we got some of these Cubots, which are essentially Roombas. If you look at the foundation of it, it's a Roomba. It's like it's one of those autonomous vacuums that rolls around your house and cleans up the floor, but kind of on steroids, right? This is sort of an open architecture. It's an autonomous ground vehicle, is what it is. I got the reaction there. That's great. It's really nice because this particular platform kind of bridges the gap from undergraduate instruction to postgraduate research. It's just this nice open platform, and some of the concepts that it can reinforce, like line following and a little bit of computer vision, is appropriate for like maybe a senior level capstone project or a first year graduate course. What's nice about these Cubots is that YOUser offers a lot of documentation, even some curriculum. So you can get some type of curriculum just right out of the box with these platforms. So these are really nice if you want to do any sort of coordinated, path planning or just basic line following to get a sense for what robotics is about. And then next, Naveed. And then the last thing I wanted to talk about are these guys. So these are really cool. There's no other way to put it. These are really cool platforms. They're called the YOUser Q car. It's like a 10th scale RC car that you could buy at a hobby store, but like beefed up with like thousands of dollars of modern sensors that you would find on an actual autonomous vehicle. So this is like our autonomous vehicle research platform. Now, these don't actually come with a ton of documentation. It's really, when you buy one of these from YOUser, you get some basic setup documentation, but you don't get any curriculum. Now, this platform is primarily designed for graduate level research. And to date, since 2021, so we're about 2.5 years into having this platform, it's been a fantastic platform. And the 3 or 4 faculty that I work with who are in this area of dynamic systems and control, altogether we have advised, I believe it's 8 master's theses. So that's actually, it doesn't sound like a lot, but we have very few master's students at our university. So to have 8 students working on one platform, one common platform, has been very beneficial to them. Yeah, so these cars are really cool. They've got full LiDAR, 360 vision, inertial measurement units, and all kinds of sensors and encoders. And the Jetson platform is just, you got tons of expandable I/O, so you can add your own peripherals if you want. Very, very high level, very, very sophisticated, but at the same time, the interface between this piece of hardware and the YOUser interface that allows you to talk to it via Simulink is actually very straightforward to use. So that was one of the things that the students have commented on most, is they felt that they were able to just dive right into the actual academic concepts rather than spending too much time just working out communication between the car and the host. So that's all I wanted to really say about it. The YOUser package that we put together for our lab has been hugely beneficial. The faculty have appreciated it because teaching these courses is more streamlined and more consistent. And the students as a whole, I think, have appreciated being able to kind of go straight from the lecture to just being able to reinforce those concepts with the Quanzer cube too. So I'll hand it back over to Naveed. That's all I wanted to say. Thank you for your time.
Thank you, Noah. And I think the next case study that I want to share with you is about the astronautics lab. So my colleague, Dr. Marco Madja, is going to talk a little bit. Marco, go ahead and introduce yourself.
Hello, everyone. My name is Marco Maggia. I am an assistant professor of aerospace engineering at Cal Poly Pomona. This is my second year. And today I want to talk about the astronautics lab and the vision that we have for this lab for the future. So first of all, I want to, well, my areas of expertise are small sat dynamics and attitude control, and orbital mechanics, and also vibrational control. And I do active research in station keeping of small sat around vibration points. So this is the vision that we have for the future of the astronautics lab, and especially one part of it, which is called the small sat lab, is to introduce a digital twin accompanied with hardware in the loop to boost our research capabilities and also teaching capabilities in order to provide a highly skilled workforce for the industry and make the lab more accessible. In fact, next please. This is the current small sat lab. So as I said, the small sat lab is just one part of the astronautics lab. The other one is the space lab. The small sat lab is not just small sat, it's very small itself. It's only 15 by 11 feet, and it only really comfortably can host 3 to 4 people at a time. Already for the lab is pretty crowded. So I just wanted to describe very quickly the instruments that we have right now, and then later I will describe how the introduction of a digital twin with the hardware in the loop can boost the potential of such lab. So starting from the bottom left, we have air bearings. Air bearings provide an almost frictionless surface in order to test attitude control. So you can mount a small satellite on top of the bearing. There's a high pressure air pumped through the stand, and so you can control the attitude of the small sat. You can measure the motion, you can capture the motion of a small sat, that is the position and the velocity, using the set of OptiTrack cameras. We have 4 of them in the picture. You can only see 3 of them. And we also have the capability of simulating a 3-dimensional trajectory for a small sat using the hexapod that would be on the top right corner. Hexapod, as the name suggests, has 6 legs, and it gives a limited range, but still we can simulate a 3-dimensional trajectory for a satellite. Everything it can be mounted on the smart table that also is capable of active vibration damping to minimize external perturbations. Everything is controlled by a workstation that allows us to interface all the pieces of hardware. So this is the present of the small sat lab. What do we have in store for the future? Next slide, please. Is the introduction of a digital twin. And I will explain more of what a digital twin is and how we will be using that in the context of dynamics and controls research. Of course, in order to do that, we need new equipment. So here I'm talking about the future. And Dr. Nakjiri and I wrote a proposal. So we're seeking the money from the Department of Defense, same grant that Dr. Tsuchiya won in 2021. So hopefully, if awarded in 2024, we'll be able to build a new platform. And the two big consequences will be to prepare our students to enter the industry with new capabilities and skills in digital twins, and to make the lab more accessible and to foster collaboration with other institutions. All right, so what is a digital twin? So a digital twin, you have to think about it as a virtual replica of a real system. So in our case, the real system is a small satellite. So the digital twin, you're modeling the real satellite, but in a simulated environment. So you can replicate the behavior, functionalities, and responses of the actual hardware through a simulation. Traditionally, what you would do is to build hardware and test it. So now we are on the other side of the spectrum. We simulate everything virtually, but we can find a midway between pure testing, experimental testing, and pure simulation. And that's where the hardware in the loop comes to play a role. So the hardware in the loop potentially could be the whole satellite built. But in order to build a whole satellite, it costs a lot of money, and it takes a lot of time. So instead of replicate the entire system physically, we substitute just, we have alternative hardware that emulate just parts of the satellite. In our case, we would add sensors and actuators and control system in order to study the attitude and dynamics of a small sat. So we don't need necessarily to have the whole satellite itself. We just have the actuators and the sensors. And I'll show later how Quanzer designed the system. This is very useful because it allows us to exchange in real-time data between the simulation and the hardware. And it allows us to validate in real time the responses of the simulated system. We can verify with the actual hardware and vice versa. So that cuts a lot of cost, a lot of time for testing, validation, and that allows us to design iteratively in a much faster way rather than having to build every time a new piece of hardware. And in case it's also allows us to mitigate the risks, because let's say that in the simulation we see that the hardware breaks. Well, it's just simulated. We haven't really broken anything. There are several ideas for the research that deal with digital twin and hardware in the loop. I listed there 3 ideas. The first one would be just to build the test platform for attitude dynamics. Then we could potentially look into formation flying. And formation flying means multiple satellites. Of course, in reality, that would mean a lot of space, a lot of money, but we could replicate that virtually, saving all that. And finally, we can develop robust control algorithms capable of adapting to unforeseen disruptions such as cyber attacks or system malfunctions. Next. So this is the envisioned system that we designed with YOUser. So at the bottom, we see there's the digital twin itself, so the simulation, and it's basically just a very powerful computer that allows us to recreate all the space environment and the model of the spacecraft itself. And at the top, we have the hardware in the loop. So we have two platforms. On the left, we have the so-called sensor testbed. So this is practically a 9 degree of freedom IMU. So we have 3 degrees of freedom covered by the accelerometer, then another 3 by a gyroscope, and then a 3 degree of freedom magnetometer. So this represents the sensors. And then we have the dynamic test bed. So we have 3 degree of freedom gyroscopes, and each unit emulates a reaction wheel. So those would be the actuators that actually control the system. So you see, we have the digital twin paired with the hardware in the loop. And this is going to be our pilot program named Iron Bird. Next, please. Okay, so why do we want to do this? Why do we want to focus on digital twin? Well, as Naveed and Nolan said, the industry calls for it. When we meet with our industry partners, they tell us, well, we're looking for certain skills for new engineers. And in particular, digital twin and hardware in the loop technology is really sought for, as well as model-based system engineering capabilities, and thirdly, also machine learning and artificial intelligence. So this comes from not just the private sector, but also the public sector, such as NASA and the US Space Force. So how can we help the industry get this highly skilled workforce? Well, first of all, we need to procure the equipment and make an effective environment in which we can conduct research. Then we have to integrate the concepts of digital twin, hardware in the loop, and model-based system engineering in the curriculum by adding these topics to existing courses or form entirely new courses. Then we have to get the students to practice, to learn by doing. So that could be part of courses or their undergrad research through senior projects or through research that they do with their clubs that run in parallel with the courses that we teach. And finally, the lab can be used in partnership with the industry itself. So we can send students for internship, or we can work in collaboration, so joint project with the industry. And so we're ready to roll the students in the industry, hopefully well prepared. And finally, switching from a more traditional lab in which you need to be there to conduct the experiments to a virtual lab, thanks to the digital twin, well, that has a lot of advantages. Well, first of all, you can access the lab pretty much virtually 24/7 from anywhere in the world. So availability is increased and accessibility is increased. Then you can have a more flexible experience when it comes to learning and research, because again, the simulation can be run from anywhere. And it also guarantees more continuity in learning and research. Let's say something happens like another pandemic, hopefully not. But in case, if everything is shut down, you can still do research and run experiments remotely. It's more cost effective because you don't actually have, as I said earlier, you don't have to build new hardware. You can just run simulations. In this scenario, you would probably just use the digital twin alone rather than paired it with the hardware in the loop. But either way, it boosts the chance to be more flexible and more productive in our research. And also, it fosters collaborations with other institutions, because now other institutions are maybe far away. They can access our facilities without actually being there. And yeah, so to recap, being able to install a digital twin platform is going to be very useful to boost our research capabilities, and in turn that will allow us to develop a high-skilled workforce and make our lab more accessible. So this is my case for the digital twin. So hopefully we will get the money to do so. So back to Naveed.
Thank you, Marco. So the last part of our case study, which I'm going to go over it as on behalf of Dr. Mirzai, who is a professor and chair of industrial and manufacturing engineering at Cal Poly Pomona. She has expertise in machine learning, mathematical programming, and over the past few years, she served as a faculty fellow at Edwards Test Center, and looking into the application of mathematical modeling and improving target tracking and generative AI for manned and unmanned aerial vehicles. So she is leading an effort, again, sponsored by Quanser, to create something that we call a smart manufacturing lab. So I want to share some of the objectives over here. This is, again, a future plan. So this is, we are showing where we are headed. We are basically looking into creating an adaptable lab solution that looks into emerging technology across different platforms, especially across things that are taught in different courses at Cal Poly Pomona. So what they are doing with Quanser is that they are creating some sort of a cutting edge technology factory technology that looks into open platforms and flexibility. They are looking into creating or basically bringing equipment that aligns with what CPP requirements for teaching is, and what we want to have people trained for the industry and create industry-ready workforce. They are looking into how they can better integrate this with the current courses that they have. They have some courses in the industrial manufacturing department, so they want to see how we can bring new technologies into teaching some of the basics and some of the fundamental courses. And finally, they always think about how they can sustain the lab. And one of the reasons that they are partnering with Quanser is that they always have people that are trained to help how we can use and take advantage of these features that we have on the system. So that's one of the motivating reasons that we are working with these platforms. So the project that they started is in multiple phases. So they are in the beginning phase one, that they are looking into something that is called the storage configuration solution. This is kind of a state-of-the-art technology components that goes into this lab. So you see that we are designing the entire lab around the idea of how we can improve the learning experience for for the students and bring the industry demand into teaching the courses and teaching the technologies to our future engineers. So what you see over here is just kind of an overall vision for this lab. But there are a few elements of this lab that we are highlighting over here as kind of showing you the plan. This is looking into different elements of the manufacturing line. So you see that they're looking into retrieval systems. So the robots that they can, go and bring parts and also sort parts into different shelving. So these are different elements that you see over here. We have the Cubot platforms that are basically designed and being programmed for doing especially this task. On the other picture, you see the Q arms. These are helpful for doing the assembly and also for doing this part of sorting and retrieval systems that they can, manage different elements that goes on the conveyor belt. And students can, program these because these are open to any sort of algorithms that they want to, implement on it. So students can experiment with different types of optimizations in terms of their processes, and these platforms can create something that is very similar to what students are going to see on the actual factory line and in industry. So this is part of what the IME department is very interested to explore. This is the assembly lines. Again, you can use the same type of equipment for a different purpose, for a different course. When students are looking into how they can optimize assembly line, these platforms can, work on different elements. So this is a PCB assembly line, for example, that they're envisioning for this lab. And these Q arms, they can be programmed, and they have all the sensors to be able to provide feedback to the students, and student can optimize based on that. And they can, run different types of methodologies on it to understand how it impacts the overall manufacturing line, because you're not just looking at one equipment, but you're looking at the entire process through these equipments. And finally, again, you look at the entire, platform together. So you can, do assembly, you can do retrieval, you can do sorting. So you can, some of these robots can bring the elements or the pieces to the assembly line. The assembly line can, then pass it to the sorting, and the sorting can pass it to the storing. And you can see all of these within the same equipment that they are bringing into this lab. And one of the main reasons that they're investing on this is not just to do practical or, let's say, typical type of algorithms that are used in industry, but they're also going to use this platform in order to research into how machine learning and artificial intelligence can help us to design better manufacturing line, assembly line. And because of the type of platforms that they are getting into this lab, they're capable of doing this in an open architecture format. So this is just the last slide for the IME department, showing different courses. As you can see, these are the courses that we have at the undergraduate level, and are looking at how this equipment and these labs are going to help these particular courses, and what are the configurations that they're going to use between all of those different elements that we saw in the pictures. And as you can see, even just one lab can be integrated into a lot of different courses. And as I said, it can also be useful for the research into the future algorithms and how we can develop these smart manufacturing platforms. So this is, again, another vision that came out of a lot of industry-driven conversations, that what the industry wants the student to know when they come out of this program, and they understand not just on the theory what is the process that goes into the manufacturing, but actually seeing the manufacturing line and assembly line and working on algorithms, working on optimizations. And that's well fitted within the scope of what we do at Cal Poly Pomona. I'm going to go to the closing slide and just giving you an overall view of what we talked about. So Cal Poly Pomona philosophy of learn by doing, and how it is kind of motivating the teacher-scholar model for doing research and teaching at the same time, But one of the main elements that is always important in anything that happens between that philosophy and the goal and the vision and what we apply in the classes, which is that teacher scholar model, is always comes from the industry inputs that we have. And we try to take them very seriously. We change our curriculum on a very frequent cycles. Every time that we have a meeting with the industry and there is a new project, we think about how we can improve what we do in the classes for the students. But in today's discussion, we also talked about 3 core elements that comes out of those industry inputs: the model-based and digital twin, which we are trying to create a better workforce for industry to align with what the current trend in digital twins and digital engineering is. We talked about the virtual labs, how we can use some of these platforms to be able to run algorithms, even run algorithms with the hardware in the loop, but virtually, and allowing more access and basically what we call supporting student success in teaching and research at Cal Poly Pomona. And we are also talking about smart labs that are capable of giving us the ability to do innovative research. And by just a few equipment, we can allow students to be creative as long as the platforms are open. We can go and explore new algorithms. We can look into machine learning and AI and what we can do in terms of preparing students to go into the workforce for the future of industry. So that's kind of a wrap up for my slides. I know that we went through some of the examples very quickly because there are a lot to discuss. We wanted to just give you a glimpse of what we are doing at Cal Poly Pomona, but I always encourage you to come back to us and either collaborate with us to create a better vision, or we are happy to share our experience, and maybe that's something that you want to implement for your institution. So with that, I'm going to just thank you all for joining us today and also watching this later online. And if there is any discussion, any questions, we welcome that at this point.
Perfect. Thanks a lot to all our presenters for that amazing presentation. It was very informative. I think we can proceed to answer the questions that may have come in from the audience at this point.
The first one in the chat, I feel like is directed toward me. So maybe I'll take that one. What feedback do you have for educators who essentially say that the building of the plant and the building the interface between the plant and software, that's part of it? We totally get that. But in a 15 weeks semester, there's just finite time that we have in the lab. So prior to having the Quanser set up, a large majority of time was spent by students just troubleshooting their whatever plant they're trying to build, designing it, building it, troubleshooting. And in many cases, they never actually got to do control. Like, they spent most of the time building, troubleshooting the plant, getting the ins and outs to work, getting, learning about sample rates, Nyquist, Nyquist periods and so forth. So it was a big challenge. And so we kind of went to the other end of the spectrum. So now we're completely sterile, if you will. We've got, pristine turnkey labs, which some of you say, like, I believe the question came from Mehdi. It could be seen as there's a gap there, that students are missing that little piece of having to struggle through the build process. So actually what some faculty are doing, we have, academic freedom to teach these classes essentially how we'd like. Some faculty are incorporating a project element as well. So maybe I think one faculty is doing every other week, they'll go into the lab and do, reinforcement exercises on the Quanser equipment. And then in the off weeks, they'll be working on their final project, which is generally, stabilizing some type of unstable system using various methods learned in the lecture. So hopefully that answers your question. It's not all or nothing. In my experience, I have appreciated going with the full Quanser experience, but now that I'm comfortable and we've written the curriculum for this lab, I'm thinking about incorporating a sort of project element to this as well. The other questions, I don't know. Maybe one of you guys could take. I also see that there's a hand up in the participants window. So
Yeah, our second question is, could you elaborate on the specific challenges faced in integrating industry-driven tools like using Quanzur's software, Quark, and MathWorks into your curriculum, and how these challenges were addressed?
Okay, that's an interesting question. It's more on the logical side. So I think Nolan and I we went through some of these challenges, but I think from the university perspective, what we are trying to to do is to keep up with the pace of industry and changing what they need and skills and things like that. But universities are usually much slower. So trying to get new technologies into the university goes through a lot of processes and approval. But one of the challenges is always finding basically the right partners and trying to push this through different channels. If it is coming from industry that says that this is what you need to do for our program, that's usually a very strong voice. And we can take that to our leaderships, we can take that to our dean and other people at the university and make a case. Of course, funding for universities like us is kind of another challenge. So we are trying to always be efficient in terms of how we are spending our money, especially because we have a very large demand on teaching. So we have to always think about the running cost of teaching classes and what we are going to do in the future, in a few years, how we are going to maintain these labs. So those are some of the things that we try to always keep in mind when we are looking into how we can integrate some of these new technologies into our lab. But something like MathWorks platform, MathWorks is already integrated in a lot of courses, so it's very easy to add on to it. Now Quanzur is getting much more presence at Cal Poly Pomona in different departments, so that helps too, because now we have a proven record that the system can help students. So those are usually great experiments for us to have a partner, work with the partner, and then after that we decide what we can do in the future with those platforms. And that has been very at least positive to me working with MathWorks and Quanzur so far. Nolan, is there anything that you want to add to that?
Well, Naveed, you talked about very high level stuff, just like getting sort of approval to adopt MathWorks and Quanzur products into our curriculum. Beyond that, like once we have that, there's also day-to-day kind of challenges. Most faculty who teach controls and dynamic systems are pretty versed in MATLAB and Simulink, the software. But for me, like the frontier, the boundary for me, like I've interfaced with hardware in the past, but there is a little bit of a learning curve to incorporate in Quark, which is sort of the Quanzur interface between hardware and software. So it was for me anyways, the first time I taught the class using the Quanzur stuff, there's a little bit of maybe a couple of sessions where it's a little bit rough because some of the hardware wasn't talking to the software. And so there's a couple of elements there. You want to have, like whatever your institution is, you want to have a good relationship with your IT people. I've made it a point to go to just like foster a relationship with our IT people, because they'll, if you call them, they can troubleshoot a lot. And then also on the Quanzur end, I had a contact who was very easy to interact with. I had his personal cell phone once he came out to do training. So, during a lab one time, I just texted him and said, hey, a couple of these workstations aren't talking to the hardware. What do you suggest? And he just, wrote back with like a list of things I can try, and then one of them actually worked. So a little bit of a learning curve, but I will say that you can certainly reach out to folks at Quanzur or your IT department to help with those specific day-to-day challenges.
That's awesome. I'm glad we were able to help where we could. Before we go to the next question, I would like to point out all the attendees in the audience for the webinar are muted by default. So if you have a comment or a suggestion, please feel free to put that in the chat, and we'll be able to address that. Our next question is, could you share an innovative experiment conducted using a Quanzur product that goes beyond the standard procedures and presents a unique challenge?
Is that me again?
I think you probably had more experience with doing research with those.
Well, my mind right now goes to the Q cars. We've had several master's students doing their thesis work using the Q car platform. Just yesterday, we had a defense, one of our students presented on his work using model predictive path integral control for the Q cars, which is, to me, like right at the frontier of new research, which is very interesting. And the challenge there is that there's certainly an active area of research, but certain things have not been tried. Certain things have been proven in theory, but not applied. So the challenge with all sort of academic research is validating, academic findings. And this was a really interesting one because I was on the advisory committee for this particular student, and I really had to dig deep and go back into my research day, my PhD days, where I was doing receding horizon adaptive control to be able to offer the student any useful advice. So one of the things that this Quanser Q car platform allows is basically it's just this playground to be able to explore in many different directions. And of course, the challenge with that is the advisors have to be ready to sort of engage with that level of research and try and help these students wherever we can. So that was a really interesting project. And, we've got several other master's projects along those same lines. So the challenge is for us faculty to, not just give the students the hardware, but also stay relevant and up on our literature so that we can help them in a meaningful way.
Thanks for the answer, Nolan. While we're waiting for the suggestion, we have another question here. Let me just get to it. Let's see. Chat. Could you elaborate on the specific challenges faced in integrating industry-driven tools like Quanser and MathWorks into your curriculum, and how these challenges were addressed?
Yeah, I think we addressed that one already.
Oh, I read that twice. How does CPP ensure the balance between teaching fundamental engineering principles and incorporating cutting-edge industry tools, considering the rapid evolution of technology?
I'm sorry, is that in the chat or just a general?
That came through chat directly.
Oh, I see.
So
Yeah, go ahead.
maybe something that I can share on that. So what I think one of the reasons that we have this strong relationship with industry is because of that, because we want to see where the industry is going. And through these relationship that we have with our partners, with our IAC, Industry Advisory Council, or committees, we basically get informed of what we are trying to do. Is it aligned with what the industry wants to see? And it's through those communication channels that I maybe shared at one of the slides that we try to be engaging with our industry partners in many different occasions and different ways. And learning about what they need, again, gives us the upper hand to go and make a case to our basically administrations and say that this is what we need to do for the program in order to keep up with the changing industry. So we have been very successful, at least in the engineering programs over here at Cal Poly Pomona, because a lot of our projects are sponsored by local industries. A lot of our students work as interns or get a job at local industries, and they come back and try to bring more support from industry to the campus. And through those relationships and interactions, we try to understand what they need. And these direct relationship helps us to actually plan for the future of the lab. So Cal Poly Pomona is a little bit unique in terms of how we are looking into research. It's not completely fundamental research that you want to do what you think is going to be the future of industry in 50 years. We are basically working with the industry partner to identify what is needed right now and how we can bring that in terms of the project and research into a classroom and also into our projects. And students are going to go through that. So not sure if I answered everything that you asked, but I think majority of our developments in upgrades of the labs and developing new research labs and things like that are kind of based on the conversations and the direct connection we have with the partners.
Perfect, thank you. While we wait for the suggestion, there is one more question that came through direct message. Can you speak more about the anticipated impact or measurable outcomes these curriculum developments and industry collaborations are expected to have on students' readiness for real-world engineering challenges?
Yeah, I think like most departments in the College of Engineering, we've got an IAC, or our industry action committee or something like that, where we've got both alumni as well as just industry partners that come once a semester or once an academic year to just talk about what they're seeing with recent graduates, and they provide us with like a lot of insight onto what is missing or what are the strong points of our students coming out, fresh graduates. And one of the things is just a lot of local industry likes to hire from our university because they feel that our students tend to be able to hit the ground running more than others. And a lot of that comes down to just the activities that the students are doing in the instructional labs. In my area in particular, dynamic systems and control, a lot of students go into defense or aerospace or anything really that requires that knowledge of dynamic systems and control. And in that space, there's basically a couple of choices. You've got LabVIEW or you've got MATLAB and Simulink, and it seems like there's a majority of local industry that would rather have students versed in MATLAB Simulink be able to hit the ground running. And so our efforts to incorporate that software consistently through a series of classes is one of the things that I think really impacts the readiness of students right as they graduate. I don't know if you have anything to add to that, Naveed.
Yeah, I think that's the way that you explained it. That's a great way of looking into how we are assessing the impact through our again connection with the industry and looking at the alumni surveys and things like that. But we also try to do some experimentation on our own classes too. So some of us are active in doing some research in terms of teaching classes and experimenting with different tools. For example, what we are doing right now with the Quanzer equipment in the feedback control lab, we are comparing it to the result of what we had before and trying to understand how the students are feeling after getting these classes and going through this experience from a direct basically data point, and how students are doing better in the future classes after taking this class. Is it going to improve that particular thing? So this is kind of what we do as part of our assessment of the programs. So we are ABIT accredited program. So through this cycles of ABITs, we have to look at all of these data and see how it improves. And we try to see how the equipment, how these connections with the industry is going to improve the student outcome from the program. So I think that's kind of our approach in general. So looking at both direct and indirect type of assessments to understand how it impacts the student's outcome. Yeah.
That sounds good. I would like to thank all the speakers. I know we are running over time. If you have any additional questions, please feel free to email us, and we'll take those as we can. If you have any questions after this webinar, please visit www.quanza.com or email info@quanza.com as well. We'll be happy to chat with you. Last but not least, thank you again for joining us today. Thank you, Naveed, Marco, and Nolan. That was a very good presentation. Cheers.
Thank you.
Thank you. Bye-bye.